If you watched Thursday's video, the 937 galaxies, the galaxy that existed 280 million years after the Big Bang, the black holes that grew too fast, the universe that gives two different answers about its own expansion rate, then you already have the data. Here is the hypothesis that connects all of it. It was published in Physical Review.D, not a blog post, not a thought experiment, the most respected physics journal in the world. And the claim it makes, if confirmed, means our Big Bang was not a beginning, it was a bounce. Let me be precise about what this hypothesis actually says. It does not say we are trapped inside a rotating, crushing black hole. It does not say we are being spaghettified. It does not say the laws of physics are different here. What it says is this: when a massive enough object, a star, a gas cloud, collapses under its own gravity, the standard model predicts a singularity, an infinite point of density, where the equations stop working. But quantum mechanics disagrees. At the smallest scales, the quantum exclusion principle prevents things from being compressed into a single point. The same principle that prevents electrons from occupying identical quantum states, applied to the entire mass of a collapsing object. What happens instead? The collapse slows, stops, bounces, a gravitational bounce. And from inside, from the perspective of what is now expanding outward from that bounce, that moment is indistinguishable from a Big Bang, exponential expansion, a hot, dense beginning, everything that followed. From outside, in whatever universe contains this black hole, you would see nothing unusual. A black hole formed. The matter disappeared behind the event horizon. End of story. But inside the event horizon, inside what looks, from outside, like a black hole, a universe was born. That is the hypothesis, not fringe physics, not science fiction. A paper published in Physical Review.D in 2025, authored by physicists at the Institute of Space Sciences in Barcelona. The paper is titled Gravitational Bounce from the Quantum Exclusion Principle. The lead author, Enrique Gaztañaga, is a cosmologist at the Institute of Space Sciences in Barcelona. This is not speculation at the edge of physics. This is peer-reviewed, published, and it makes specific, testable predictions. Here is what the model proposes. When a region of space collapses under its own gravity, massive enough to form a black hole, the quantum exclusion principle halts the collapse before infinite density is reached. The mass bounces, and the bounce drives exponential expansion. That exponential expansion is what we call inflation, the rapid expansion that smoothed the early universe and seeded the structures we see today. In the standard Big Bang model, inflation requires a separate entity, a theoretical field called the inflaton. That has never been directly detected. In this model, inflation is automatic, a consequence of the bounce, no extra physics required. But here is where it becomes testable. If our universe began as a gravitational bounce inside a black hole, the mathematics predicts a specific, observable signature, a small but non-zero positive spatial curvature. The universe is not perfectly flat. It curves very slightly, like the surface of a vast, closed sphere. Not enough to close the universe over the distances we can currently measure, but enough to be detected by the right instrument. If you watched Tuesday's video, you already know what that instrument is. Go back to Thursday's video, every anomaly James Webb found, and look at them through the lens of bounce cosmology, the 937 galaxies. In the standard Big Bang, the early universe should have been cold and diffuse. Structure took time to form. Stars ignited slowly. But if the Big Bang was a bounce, if the initial conditions were set by the physics of a collapsing object, not an arbitrary singularity, you get a different starting point. More concentrated initial structures, more turbulent initial conditions, more consistent with 937 galaxies already forming stars at rates our models call improbable. MOM-Z14, the galaxy that existed when the universe was 2% of its current age, already chemically evolved. Stars had already lived, died, and seeded the galaxy with heavy elements. Bounce cosmology does not automatically explain this, but it gives the universe a head start. The initial conditions are more organized, more structured, more consistent with early galaxy formation than a cold, undifferentiated singularity. And the black holes, the objects too massive for their age. In bounce cosmology, the initial mass distribution after the bounce would be different, more concentrated, more capable of seeding massive structures quickly. None of this is confirmed, but every anomaly James Webb found is more consistent with bounce cosmology than with the undisturbed standard Big Bang. The data does not prove the hypothesis, but it does not contradict it. And in science, that matters. But the clearest connection is the Hubble tension. 2 measurements, 1 universe, 2 answers. 67 kilometers per second per megaparsec from the cosmic microwave background, 73 from nearby supernovae, 5 sigma. Not noise, not error, real. Here is why bounce cosmology is relevant. The CMB measurement probes the very early universe, the first 380,000 years after the Big Bang. The supernova measurement probes the late universe, the last few billion years. In the standard model, these 2 eras should follow the same expansion history, one clean curve, beginning to end. But if the Big Bang was a bounce, if the universe's earliest moments were governed by the physics of a collapsing black hole, the expansion history may not be one clean curve. There may be a transition, a point where bounce physics dominated and standard expansion took over. This does not solve the Hubble tension automatically, but it offers something the standard Big Bang has struggled to provide, a physical reason, a mechanism, why the early and late universe might behave differently. But there are objections, and they are serious. The first, inside a black hole, tidal forces are extreme. Matter is stretched, spaghettified. So how are atoms intact inside our universe? The answer, tidal forces in a black hole depend on its mass. For an object massive enough to contain an entire universe, the tidal forces at the event horizon are not extreme. They are negligible. A large enough black hole has tidal forces at its boundary so small you would pass through without noticing. The same physics that makes stellar black holes lethal makes universe-scale black holes survivable. The second objection, we see the universe uniformly in every direction. That is called isotropy. Inside a black hole, you might expect a symmetry, a preferred direction. This is a genuine challenge. The paper addresses it through the inflation that follows the bounce, which smooths out any asymmetry, but it remains an active area of research, not solved, being worked on. The third, if we are inside a black hole, what is outside? That the hypothesis cannot fully answer, not yet. It predicts the structure of what we would observe inside. What the parent universe looks like remains unknown. These are real gaps. They are why this is a hypothesis under active investigation, not a confirmed theory. But here is what should actually keep you awake. If our universe began as a gravitational bounce inside a black hole, then every black hole our universe has ever produced may be doing the same thing. On the other side of every stellar collapse, on the other side of every supermassive black hole at the center of every galaxy, a new universe is expanding, with its own stars, its own galaxies, its own incomprehensible span of space and time, invisible to us, separated by an event horizon we will never cross. This is not speculation without foundation. It is the direct consequence of a hypothesis published in Physical Review.D, taken seriously by theoretical physicists for decades. The physicist Lee Smolin at the Perimeter Institute in Ontario formalized it in 1992. He called it cosmological natural selection. And his version adds one unsettling element. Each new universe is born with physical constants slightly different from its parent. The constants that determine the mass of electrons, the strength of gravity, the speed of light, and the universes that produce more black holes, which produce more new universes, are more likely to propagate their constants. This is natural selection, applied not to species, to universes. If Smolin is right, and it remains a hypothesis, not a confirmed theory, then our universe is not an accident. It is the descendant of universes that were efficient at making black holes. We exist because our physical constants produce stars that die as black holes. We are here because collapse is productive. Here is what makes this different from philosophy. The hypothesis makes a prediction, specific, measurable, testable, small positive spatial curvature, a universe that curves slightly, in a way the Roman space telescope can detect. That telescope, the one from Tuesday's video, 100 times more powerful than James Webb, launching in 5 months. With the ability to map 35% of the entire sky and measure the curvature of the universe directly. If the curvature is flat, 0, the standard Big Bang survives intact. If the curvature is slightly positive, consistent with what Gaztañaga's paper predicts, then everything we thought we knew about how the universe began needs to be revised. We will know within our lifetime. Not eventually, not someday, within 5 years. The 937 galaxies that current models cannot explain. The galaxy that formed before our models allow. The black holes that grew too fast. The universe with 2 expansion rates. All of them pointing to the same answer. Our universe, every star, every galaxy, every atom may have begun as the inside of something that looks, from outside, like nothing should ever escape. And if that is true, then right now, inside every black hole we have ever found, another universe is beginning. The universe does not owe us an explanation, but it is giving us one anyway. If this video connected something you didn't expect, subscribe to Untold Universe, Tuesday, Thursday, Saturday, every week. Earlier I asked, if the evidence keeps accumulating, is that enough? Now you have seen why it matters, because this is not just a question about physics. It is a question about what kind of thing our universe is, whether the black holes we see are endings or beginnings. Drop your answer below. I read every comment.